Today let's talk about bases other than 10. In the decimal system, every place value is based on 10. In algebra, every value is based on x. But there are other bases. We'll examine base 2, which is the binary system, and it uses two digits, 0 and 1. Base 4, which uses four digits, 0, 1, 2, and 3. Base 8, which uses 8 digits, 0 through 7. And base 12, which uses 12 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And because this is in base 12 and we don't have numbers for 10 and 11 in base 12, we use the capital letter T for 10 and the capital letter E for 11. Let's take a look at a table that shows all of the numbers through 16. So it's the first 17 numbers in each base. So first of all, let's look at base 10. This is very familiar. It's the base that you have learned to count with, that you've grown up with, that you've become used to. It starts with the number 0 and goes through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And you could keep counting on forever, but we're only going to look at the first 17 numbers. Let's take a look at base 2. These are exactly the same first 17 numbers, and you can see they go 0, 1, 10, 11, 100, 101, 110, 111, 1000, 1001, 1011, 1100, 1101, 1110, and 1111, and then it jumps to 10,000. Then in base 4, we look at the first 17 numbers, and they are 0, 1, 2, 3, 10, 11, 12, 13, 20, 21, 22, 23, 30, 31, 32, 33, and then it jumps to 100 because there are no 4s in base 4. In base 8, we count 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, and then 20. And it goes on from there in the same pattern. And finally, base 12, the first 17 numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, T, E, and then it goes 10, 11, 12, 13, 14, and so on and so on. This table can be found in your course library. So if you find that you need to refer to it later, go to your course library and you can print it out. Now we're going to take a look at how we're going to use these bases. Notice also across the bottom of each one of these tables, notice that 16 base 10 is the same as 10,000 base 2, which is the same as 100 base 4, which is the same as 20 base 8, and which is also the same as 14 base 12. All those numbers are exactly the same number, just in different bases. Most of us have never operated in any other base except base 10. To tell when another base is being used, subscripts, and the word sub means under, are used to denote the base. In base 10, these subscripts are understood, but they could be written with a subscript of 10. The number 143 would be written as 143 with a little 10 that's down below the baseline of the number, and that 10 is called a subscript. So we call it 143 base 10. Notice that again from the slide before, 16 base 10 is the same as 10,000 base 2, the same as 100 base 4, the same as 20 base 8, and the same as 14 base 12. Let's talk about changing from a different base to base 10. In this assignment, you're going to be changing numbers back and forth. You'll be given numbers in a certain base and asked to find out what it is in base 10. And then you'll be given a number in base 10 and asked to convert it to a different base. And so I'm going to show you how to do both of those here so that you'll be ready for your assignment and be able to do this. First of all, a little bit of background. To change one base to a different base, the key is the place value. Recall exponential notation, where we separate the number, which is how many, from the place value, which is what kind. This notation helps to distinguish the number from the place value. In base 10, we have what we call decimal street. The numbers in base 10 go from 0 to 9. The place values in base 10 are based on 10, and they are 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on and so forth. Those are the place values. 156 in base 10 is written as 1 times 10 squared plus 5 times 10 to the 1 plus 6 times 10 to the 0. And it would be shown like this. So we have a block, which is 10 squared. We have one of those. We have 5 of the bars that are 1 by 10, which is 10 to the 1. So there's 10 little blocks there. We have 5 of those, so that would be 50. And then we have 6 of the little 10 to the 0 blocks. Remember that 10 to the 0 is just 1. So we have 6 of the little 1 blocks. In base 4, we have quad street. The numbers in base 4 go from 0 to 3. Place values in base 4 are based on 4. They are 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, and so on. 312 in base 4 is written as 3 times 4 squared plus 1 times 4 to the 1 plus 2 times 4 to the 0. Now you'll know which exponent to start with because you should always end with the 0 exponent. And it looks like this. So we have 3 little blocks that are 4 squared. They're 4 up by 4 across, which makes them 4 squared. So we have 3 of the 4 squared blocks. We have 1 of the 4 to the 1 block. So it's a block that has 4 little 1 pieces in it. And then we have 2 of the 4 to the 0 blocks. Remember that 4 to the 0 power is 1. Anything to the 0 power is 1. So we have 2 of the little 1 blocks. So this looks like 312 in base 4. How many little blocks are there? Can you see it? You might want to pause this slideshow for just a second and count the number of blocks there are, because that number will pop up again in the slideshow, and it will make sense to you when it does if you'll count them. All right, it's time for our examples. Let's look at example 1. Let's change 312 in base 4 to some number in base 10. Now this is the number we just had on the previous slideshow. You saw what it looked like in base 4. What you are asking is how many 10 squareds there are, how many 10 to the 1 power there are, how many 10 to the 0 power there are, and so on. So we're changing to base 10. So we want to know how many of each of these there are in that number. To find out, follow these steps in order, and you may want to write these steps down until you get used to using these steps. Step 1. Write 312 base 4 in exponential notation. So we write it 3 times 4 squared plus 1 times 4 to the 1 plus 2 times 4 to the 0. Step 2. Change the place values from exponents to their number form. So we take 4 squared and change it to 16. Take 4 to the first power, change it to 4, and take 4 to the 0 power and change it to 1. So now we have 3 times 16 plus 1 times 4 plus 2 times 1. Step 3, multiply each number by its place value. So I multiplied 3 times 16, and that's 48. 1 times 4 is 4, and 2 times 1 is 2. And finally, add them all together. 48 plus 4 plus 2 is 54. If you took the time to count the little blocks on the last slide, you probably counted 54 blocks, didn't you? Well, that's the number in base 10. So 312 in base 4 equals 54 in base 10. Now let's take a look at example 2. Let's do this one more time. This time, let's change the number 5008E2 in base 12 to some number in base 10. We're going to follow the same steps. Step 1, write 5008E2 base 12 in exponential notation. You simply expand it out with your exponents of 12. So 5 times 12 to the third plus 8 times 12 to the second plus e times 12 to the first plus 2 times 12 to the 0. You always want to end with a power of 0. Step 2, change the place values from exponents to number form. So 12 cubed is 1,728, 12 squared is 144, 12 to the first power is 12, and 12 to the 0 power is 1. So we just changed each one of those. The third step, multiply each number by the place value. So 5 times 1,728 was 8,640, and 8 times 144 is 1,152. And E, which remember E stands for 11 in base 12, E times 12 is 132, and 2 times 1 is 2. Then finally just add them all together, and you'll get 9,926 base 10. So 5,008E2 base 12 equals 9,926 in base 10. Okay, let's do this in the other direction now. Let's change 54 in base 10 to some number in base 4. Now you've already seen this, you know what the answer is, but let me show you how we find this answer. What you're asking is, how many 4 cubes, or the number 64, because 4 cubed, 4 times 4 times 4 is 64. So how many 4 cubes, or 64, there are, how many 4 squareds, or 16, there are, how many 4 to the first powers, or 4, there are, and how many 4 to the 0 powers, or 1, there are. That's what you're really asking here. Well, to do this, we're going to follow these steps. Set up a division problem, like the old-fashioned division problem that you're used to doing way back in grade school, where you have the little division bar. You put 54, which is the number in base 10, inside the division bracket, and we're going to put 64 on the outside. Now, why did we choose 64? Well, because that's the biggest number in base 4, 4 cubed. 4 cubed is 64, so we started with that. So we're going to divide 64 into 54. Well, 64 won't go into 54 because 54 isn't big enough. So it goes in 0 times. 0 times 64 is 0, and we subtract 0 from 54, and we have 54 left over. So in other words, there are no 4 cubes in this number. But we take the remainder, which in this case is 54, and we put it into the next division problem. Or you could have started with 4 squared if you knew it was going to be 4 squared. If not, start with 4 cubed, and you find out there are none of those. Take the remainder, take it up to the next division problem, stick it back in the division problem, and this time we're going to divide 16 into 54 because 16 is 4 squared, and 4 squared is the next smallest exponent. 16 goes into 54 3 times, write the 3 on top. 3 times 16 is 48, write that underneath the 54. Subtract 54, subtract 48 to find your remainder, which is 6. The remainder is very important because that will become the part that we use for our next division problem. But in this case, remember the 3. 3 is the quotient, and that will become part of our answer. So now we're going to take the 6, put it up into the next problem. We take 4, which is 4 to the first power. 4 to the first power is the next lowest power. We take 4 into 6. It goes 1 time. Take 1 times 4. That gives us 4. Write it underneath the 6. Subtract, and we get 2 as our remainder. So the next number in our answer is 1. Then we take the 2 and put it up into the next division problem. Then the next lowest exponent of 4 is 4 to the 0 power. And 4 to the 0 power is 1. So we take 1 into 2, goes in 2 times. 2 times 1 is 2, we subtract and we get 0. There's nothing left over. So 2 on the top is the rest of our answer. Notice now on top we have the numbers 3, 1, and 2. Because there are 3 4 squareds, 1 4 to the first power, and 2 4 to the 0 powers in the number 54. So 54 base 10 is the same as 312 base 4. And this may take some practicing to get this down, but you might want to write down this example so you have it to do your exercise. Also, on the web page where you found this video, right next to this video is a link to the lesson for this assignment, And the lesson is exactly the same as this slideshow. So you may want to use that and print this out. It will have everything in it. So you don't have to take notes and you don't have to write this down. You can just print out that lesson from the link that's next to this video. Let's take a look at one more example so you can see how this works. Again, let's change 9,926 base 10 to some number in base 12. You probably want to see how this is going to work with base 12. Now this is the same number that you saw a few slides ago, so you probably know what the answer should be, but let's take a look at how to do the work. Okay, we're going to follow these steps. So first, we start with our division problem. We put 9,926 under the division bracket, and we're going to start with 12 to the third power. You could start with 12 to the fourth power if you want to, but if you did, you'd find out that it would be 0, just like we did with the base 4 number. So we're going to start with 12 cubed. It's just kind of a guesstimate to decide, well, I think I'll start with 12 cubed. 12 cubed is 1,728, so that's the number we want to divide into 9,926. And you can do that on your calculator. Put 9,926 in your calculator first, press your division button, and then type in 1,728 and press equal. And you're going to get a decimal. You'll get 5 point something, something, something. The only number you care about is the 5. Put the 5 above the division bracket. Take 5, multiply it by 1,728 in your calculator, and you'll get 8,640. Write that number underneath 9,926 and subtract them to find the remainder. In this case, the remainder is 1,286. Now make sure that you do this work correctly and make sure you use a calculator to do this, because that remainder is very important, as you saw in the last slide. The remainder becomes the part of the division problem for the next step. So we need to keep that 5 on top, because that 5 is the first number in our new number in base 12. So now we take 1,286 and bring it up and put it into the next division problem. And we know that the next exponent will be 12 to the second power, because that's the next lowest power after 12 to the third. So 12 to the second power is 144. That's the number we're going to divide into 1,286. Do that on your calculator. 1,286 divide by 144 equals, and you should get 8 point something. We don't care about the decimal. Just write the 8 down here. Take 8 times 144 in your calculator. You get 1,152. Write that underneath and subtract. 1,286 subtract 1,152, and you get 134. Now it's important that that number, that remainder that you get after you subtract, is smaller than the divisor or the number outside the division bar. If it's bigger, you've done something wrong and you need to go back and check it, but it needs to be smaller. In this case, 134 is smaller than 144. So 8 is the next number in our number that will be in base 12. Now we take the remainder of 134 and carry it up, and it becomes part of our division problem in the next step. So the next lowest exponent of 12 is 12 to the 1, and 12 to the 1 is just 12. So we divide 12 into 134. Do that on your calculator, and you're going to get 11 point something. And remember, in base 12, we don't have a number for 11, so we use the letter E. So be sure you get used to using the letter E for 11 in base 12. Write the E up above. Take E, or 11, times 12, and you get 132. 132 from 134 is 2, and that's our remainder. We're not done. So again, we need to carry the 2 up. Well, actually, we're going to keep the E as part of our answer, and then carry the 2 up to the next division problem. And the next lowest exponent of 12 is 12 to the 0. 12 to the 0 is 1. So we're going to divide 1 into 2. 1 into 2 goes twice. 2 times 1 is 2. We put that underneath. We subtract, and the remainder is 0. So 2 is the last number in our answer in base 12. So to recap all of this, the number 9,926 base 10 equals 5 times 12 to the third power plus 8 times 12 to the second power plus e times 12 to the first power plus 2 times 12 to the 0 power. And if you put that all together, you have 5,000 8e2 base 12. And that's how you do it. All right, let's quickly wrap up this lesson. First, we learned that base 10, which is our decimal system, is the numbers that we normally use, but there are other bases, such as base 2, base 4, base 8, and base 12, which are the ones we will use in this assignment. But there are also the other bases in between. You can do a base in any number. You can do base 3, base 5, base 6, base 7. But in this assignment, we're only going to be using base 2, base 4, base 8, and base 12. We learned that the steps to change a number to base 10 are: first, write the number in exponential form using the exponents based on the base you are changing to. So if you're changing to base 4, you're going to write in exponential form using 4 to the third, 4 to the second, 4 to the first, and 4 to the 0. Then change the place values from exponents to number form. So for instance, you'll change 4 to the second power to 16. Then multiply each number by that place value and then add the numbers together, and this will be your number in base 10. We learned that to change a number in base 10 to another base, first divide by the largest power of the base you are changing to. That will divide in and leave a remainder. So if you're changing to base 4, you want to start with 4 to the third power, which is 64, and divide that in. Then use the remainder that you get from that division and divide that by the next power of the base. And it's important that you understand that the remainder is not the decimal portion when you do the division. When you do the division and you get a decimal, the decimal is not the remainder. Go back and review this lesson again to find out how you find the remainder. Once you have the remainder, then you use that remainder and divide by the next power of the base. And you keep doing this until you reach power 0. The quotients, or the answers that you get across the top, will be the number in that base that you're changing to. If you need to review this lesson, you can print it out using the link to the right-hand side of this video on the web page, or you can go back and review this video again.